It doesn't matter what your perspective on the oil and gas industry is, whether you see it as the root of economic advancement, the scourge of civilization, or just something that we're completely dependent on. There's one thing most people agree on though, and that's that fossil fuels are finite and someday that we're just gonna run out. Now, because of that, society has to look for alternatives, not just alternatives for energy, but alternatives also for the chemistry. And I'm talking about the plastics, polymers, chemicals, and so many other applications. Almost all of it comes from hydrocarbons. So any replacement has to deal with both energy and materials, which leads us to the simple question: what could replace hydrocarbons since they're so ubiquitous? The number of applications and considerations is simply staggering. But what if a partial solution, at least on the energy front, already existed? Something that wasn't necessarily experimental, not a futuristic concept that only existed in a lab, but already operating at commercial and industrial scale. My name is Richard and welcome to Ron's Industries. And today in the energy industry, we're looking at ethanol and whether or not biofuel can actually replace gasoline at scale. So ethanol is actually the same alcohol that you'll find in alcoholic beverages. And it was first used as a fuel back in the 1970s. It's made from organic and renewable materials, exactly as you'd expect when we think about something like alcohol. And technically, when thinking of it as a fuel, ethanol actually has a higher octane rating than gasoline. Now that matters because higher octane ratings means better resistance to knocking, and that allows things such as higher compression ratios, which leads to better efficiency in the engine. And importantly, this isn't some lab concept. Ethanol is already used, and we're talking commercially as a fuel, and at a high level, it actually looks promising as an alternative. But there's also quite a few drawbacks. Ethanol only has about 2/3 of the energy density of gasoline. So ethanol has got around about 29.7 megajoules per kilogram, whereas gasoline's got around about 45 megajoules per kilogram. Now that means you need roughly 50% more fuel by mass to get the same energy output or to travel the same distance. So from a simple point of view, that still sounds kind of acceptable. After all, ethanol is renewable, it's already proven as a fuel, so why don't we just simply scale it? This is where the cracks in the ethanol adoption start to appear. Now, the problem from an energy point of view isn't the chemistry. The problem is scale, and to a degree, it's about logistics. Now, we're going to use the United States as a reality check here. In 2022, the US produced 58.3 gigaliters, or 15.4 billion gallons of ethanol. Now, that is an extraordinary amount by any measure. But when we convert it to oil terms, that equals about 1 million barrels per day. Now, let's compare that to the reality. The US consumes close to 20 million barrels of oil per day. So even with massive ethanol production, at current levels, ethanol only accounts for about 5% of usage by volume. To replace fossil fuels by energy value, on the other hand, production would need to increase by a factor of about 30 times. That's up to roughly 30 million barrels per day equivalent. And that's only production. There's also more constraints and considerations that we need to take into account. Now, chemically speaking, ethanol is just ethanol. Compare that to octane or diesel. For the chemically minded, the oxygen looks like it's the only real difference. But in practice, fuel blends actually really do matter. Ethanol is typically blended with gasoline to create different blends. Blends like E5, E10, E15, E85, E100, where E100 is 100% ethanol fuel. But here's an important consideration. The higher the ethanol content, the more corrosive the fuel becomes. Low blends like E5 and E10 behave much like gasoline. Most modern engines either can or do handle them easily. But higher blends introduce challenges, and that's what we're going to take a look at next. At higher blends, you'll often see hydrous ethanol, which means water. Now that sounds wrong, but here's the twist. The water is left over from the distillation process itself, and in the case of ethanol fuels, water can actually reduce corrosion within the engine. It actually encourages a protective oxide layer inside the engine, which slows long-term damage. It sounds kind of counterintuitive, but it's well documented and it's well understood. Now, when it comes to ethanol, climate matters, but not in the way that you might be thinking. Ethanol is harder to ignite than gasoline, so at high blends like E85, you start seeing issues with ignition below 11 degrees Celsius. To operate below freezing or 0 degrees Celsius, ethanol content needs to drop below E70. So ethanol, not only does it affect things such as engine design, ethanol demands specific climates and still relies partly on gasoline. And so far we've only talked about petrol engines. What about diesel? Now, diesel engines use compression ignition, and yes, they can use ethanol. Now, blends like ED95 is a 95% ethanol with a 5% ignition improvement agent. And then there's E100, which is 100% ethanol. But at that concentration, cold start problems appear around about 15 degrees. And at that temperature barrier means that seasonally, there's very few places where E100 could be used year-round. In Brazil, where E100 is actually quite common, the workaround is simple. Flexible fuel vehicles use a secondary gasoline tank for startup and then switch over to ethanol once the engine's actually warmed up. More advanced systems actually preheat the ethanol, allowing starts down to as low as -5 degrees Celsius. But when it comes to colder climates, we need to be looking at even more engineering solutions. So fuel chemistry affects air-fuel ratios. E10 differs from gasoline by around about 3% in energy value and needs around about 4% less oxygen since it brings its own chemically within the fuel itself. But E100 can require as little as 62% of the atmospheric oxygen to sustain combustion. So what's the problem now? Well, that means that engine sensors and computers need to be able to adapt to the different fuels and fuel blends in real time. These aren't theoretical problems. For fuels such as E10 with only a 3% energy and a 4% oxygen difference, the engine itself more than likely can simply deal with the differences. But at higher ethanol blends, ignition of the fuel mixture starts to become the main problem. All the same, these are engineering problems, and engineering already knows how to solve them. And if engineers can already solve these problems, what's stopping ethanol from being used as the main fuel that we all use? Now, here's the surprising part. As you might have guessed, technology isn't the blocker in this case. Engines have evolved through incremental upgrades before, from carburetors, fuel injection, direct injection, turbocharging, and also hybrid integration. The combustion engine today is leaps and bounds ahead of engines from previous generations of different vehicles. Now, to that end, ethanol-ready engines are achievable. But logistically, this is where things really start to fall apart. Now, looking back at the United States that we've been looking at from the example earlier on, current US ethanol production already uses around about 36 million acres of land. Now, remember the fact that we need to scale up by a factor of 30? That's the type of thing that would require up to 1.08 billion acres of land. Now, to put that in perspective, that's about 47% of the landmass of the entire United States. Or in other words, it's basically the landmass of India and Argentina combined, just to replace oil consumption for one country. And this is still an oversimplification. Now, although ethanol itself is renewable, renewable doesn't mean that it's zero impact. When we take a wider view to consider what it would take to produce ethanol at the scales that we're talking about, we'd still end up having emissions from things such as fertilizer production and fertilizer transport, farming equipment, harvesting, transportation of crop to processing, as well as processing, and then also transportation of the final ethanol off to distribution. And then there's the risks associated with leaning on a fuel source dependent on agriculture, such as drought and disease, as well as the damage to the crops from things such as weather or pests. Crop failure at this scale would be absolutely catastrophic, and that's before further consideration to the ecosystem that would come with that sort of land allocation. Oil and gas doesn't face that vulnerability. Oil and gas deposits, they're underground. Now, ethanol works. From an engineering and technological point of view, there's no doubt about that. Flexible fuel vehicles already operate from E0 through to E100. Ethanol is a proven and also a very valuable partial solution when it comes to liquid fuels. But replacing fossil fuels entirely, it would take decades, and that's if it's even feasible, let alone possible. Dedicating nearly half of a country's land allocation to fuel production, that's not just a technical decision, that's a societal one. Having gone into the subject as we have, this isn't about defending the status quo. Ethanol has earned its place, but the scale of our energy demand and the rate at which the demand for energy is rising with emerging technologies tells us something even more important. The solution to tomorrow's energy problems might still be something that we haven't seen yet. So, what do you think? Let me know in the comments, and I'll see you in the next video.